I want you to picture something for a second. You're standing in a gym locker room, or maybe at the edge of a community pool, and you look down at your damp, bare feet.
Oh, yeah, we've all been there.
Right. There is this very specific, highly common, and honestly, like slightly uncomfortable thought that crosses almost everyone's mind in that exact scenario. You're thinking about athlete's foot.
It's just a universal human fear at this point.
It really is. Or, maybe you've noticed a strange, itchy red ring on your arm after rolling around on a wrestling mat or something. And it is so incredibly easy to dismiss these things as just everyday gym shower annoyances.
Yeah, you just ignore it.
Exactly. A quick trip to the pharmacy, you buy a tube of cream, and you move on with your life. But what if I told you that that itchy red patch on your skin is actually the battleground of a fascinating evolutionary puzzle?
Because to understand these organisms is to understand an absolute masterclass in evolutionary specialization. I mean, when you look closely at what is actually happening on that damp foot, it is not just a mild irritation.
No, not at all.
It's a highly sophisticated biological strategy, and it's playing out right on the surface of your skin, honed over, thousands of years of human history.
And that is the exact mission of our deep dive today. We are pulling from this massive stack of microbiology research, clinical taxonomy, and some seriously wild medical history to uncover the hidden world of dermatophytes.
Which is such a great topic.
It is. These are the highly specialized fungi that have literally evolved to eat our dead skin. We're going to explore how they accidentally birth the germ theory of disease, how they use chemical stealth to survive, and how our own modern behavior is triggering a massive public health crisis right under our noses.
Or right under our toes, I guess.
Under our toes, yeah.
But the history alone, it's completely counterintuitive to how we normally think about medical breakthroughs. The story of dermatophytes actually begins by destroying a myth that had been around for centuries.
A myth that's still embedded in our language today, actually.
Yeah.
So let's clear the air right now for everyone listening. There is no worm. No fungus was ever a worm. The common name ringworm is basically just a linguistic fossil that we are stuck with.
And it is a remarkably stubborn fossil, too, because it's just so visually descriptive.
Oh, totally.
If you look at a classic Taenia infection, which, by the way, Taenia is the clinical umbrella term we use for these dermatophyte infections, the advancing edge of the rash forms this raised red circle.
Like a literal ring.
Right, like a ring. So to early physicians and everyday people, it looked exactly as if a tiny worm had burrowed under the skin and was just tunneling outward from a central point.
Just leaving this trail of inflammation behind it.
Exactly. It is a very logical, if, completely incorrect assumption based on the naked eye.
Okay, let's unpack this, because the way we actually figured out the truth is where the history gets so wild. To realize it wasn't a worm, we have to travel back to the 1830s and 1840s.
It's a very different time in medicine.
Very different. So there's this Polish physician named Johann Lucas Schönlein, and he was studying a disease called favus. And from what I read in the sources, this wasn't just a mild locker room itch.
No, favus is brutal.
Yeah, it's a severe, incredibly painful, crusting scalp infection. It literally causes permanent hair loss.
That's awful.
So in 1837, Schönlein examines these thick yellow crusts, and he identifies a microscopic fungus. And he proposes that this fungus is the actual root cause of the disease.
And we really have to pause here and appreciate how radically dangerous it was to propose that at the time.
Because germ theory wasn't really a thing yet, right?
Exactly. The germ theory of disease, this idea that microscopic pathogens invade the body and cause illness, it just did not exist in any organized form.
So what did they think was causing it?
The prevailing wisdom was that diseases were caused by miasma, which was essentially bad air, or by internal imbalances in the body's humors.
Right. The four humors.
Yeah. To point at a microscopic plant-like structure and say, hey, this is eating the patient, that was medical heresy.
And to prove this heresy, Schönlein's student, a guy named Robert Remak, does something that just completely defies modern ethics.
Oh, it's wild.
He takes the fungus from a patient's crusted, infected scalp and intentionally inoculates it onto his own arm.
He really did.
He actually grew the severe infection on his own body to prove it could reproduce the disease, which, he later named the fungus Aquarian Schönleini to honor his teacher.
Today we call it Trichophyton schönleini.
Right. But I am just stuck on the absolute madness of giving yourself a severe scalp crust on your arm for science.
I mean, it sounds horrific by today's standards, but Remak was instinctively trying to fulfill what we now know as Koch's postulates, and this was decades before Robert Koch even formulated them.
He knew he needed proof.
Right. He knew that just finding the fungus on a sick patient wasn't enough. Skeptics would just say, well, the fungus was a byproduct of the diseased tissue, not the cause.
So by taking the isolated organism, putting it on a healthy host himself, and recreating the disease, he proved it.
He provided undeniable mechanical proof of causation.
Which brings us to Paris, between 1841 and 1844. A Hungarian-born physician named David Gruby takes this entire concept and just scales it up.
Gruby was brilliant.
He methodically proved that several distinct skin and scalp diseases, favus, thrush, different forms of ringworm, were each caused by completely specific different fungi.
Yes.
He was demonstrating that specific microbes cause specific diseases. But wait, I have to challenge this timeline here.
Go ahead.
We are always taught that Robert Koch and Louis Pasteur formalized the germ theory of disease in the 1870s and 1880s. Are our sources suggesting the history books are just flat out wrong? Or was Gruby's proof somehow flawed?
Well, the history books often prefer a clean narrative over a messy reality, Gruby's science was incredibly sound. He beat Koch to the core concept of germ theory by nearly 40 years.
40 years.
Yeah. But his work was met with intense skepticism by the medical establishment, and it was ultimately just buried.
On.
Part of it was prejudice. I mean, he was a Hungarian outsider operating in the elite, highly insular Parisian medical scene.
So they just ignored him because he wasn't part of the club.
That was a factor, yeah. But the larger issue was conceptual. The idea that a rash was being caused by a microscopic living organism that you could literally pluck off a patient, put under a microscope, and watch grow. It sounded like science fiction to physicians in the 1840s.
They were just too entrenched in the miasma theory.
Exactly. They just could not process the paradigm shift Gruby was offering. So his discoveries lay dormant for decades until the rest of science caught up.
That is a staggering missed opportunity for medicine. I mean, they proved it was a fungus, not a worm, decades before the world even believed in germs.
It's tragic, really.
It is. So let's move from the history to the actual biology of how these things operate today. Because one of the things that surprised me most in the research is why these fungi only attack our outer surfaces.
That's a great question.
Like, why do they stay on the skin, the hair, the nails, but they never invade our internal organs?
It comes down to two very strict, non-negotiable biological boundaries: diet and temperature. Let's start with diet. Dermatophytes secrete a highly specialized family of enzymes known as keratinoses. And these enzymes are specifically engineered to break down the tough chemical bonds that hold keratin together.
And since keratin is basically the body's armor plating, right? It's what makes our hair shafts tough and our fingernails hard, so it's virtually indigestible to most microbes.
Exactly.
I was trying to visualize this, and it's almost like keratin is a highly secure, heavily reinforced bank vault.
I like that.
Almost no other organism on Earth has the ability to breach it, but dermatophytes evolved to hold the exact, specific enzymatic keys to unlock that vault.
That analogy works perfectly if we look at the chemistry of the vault, too. Keratin is incredibly strong because it's packed with disulfide bonds.
The sulfide bonds.
Yeah, these are strong covalent bonds between sulfur atoms in the protein chain, and they create this rigid, three-dimensional structure. It is deliberately tough to act as a barrier for the human body.
So by evolving keratinases that can cleave those specific sulfur bonds, dermatophytes exploited a massive food source that nobody else could touch.
Yes, but because of that hyperspecialization, they're trapped.
Right. Once they eat through the dead outer layer of skin or the nail bed they're living in, they hit living vascularized tissue.
And they don't have the enzymatic tools to eat soft living tissue, so they simply stop. They literally can't go any deeper.
They are ecologically self-limiting.
Precisely. I mean, if you contrast that with a yeast like Candida, which is an opportunistic pathogen, by the way, not a true dermatophyte, Candida loves living, moist tissue and sugar. It can invade the bloodstream and internal organs.
But true dermatophytes are permanently locked on the dead exterior.
Exactly.
And the second boundary keeping them on the surface is temperature, right?
Yes. Human core body temperature is around 37 degrees Celsius. For most dermatophyte species, that is entirely too hot.
They like it cooler.
Yeah, they optimally grow and reproduce at much cooler temperatures, roughly 25 to 30 degrees Celsius.
Which perfectly aligns with the temperature of the outer surface of our skin, particularly our extremities.
Yes, exactly.
Especially our feet. Our feet are furthest from our core, so they're cooler, And modern humans constantly trap them in damp, dark shoes. It is like we genetically engineered the perfect temperature-controlled, humidified resort for them.
We really did create a biological paradise for them with modern footwear. That specific temperature preference combined with the closed environment of a shoe is why athlete's foot, or tinea pedis, makes up such a massive, outsized share of all dermatophyte infections globally.
You don't want your warm bloodstream.
No, they want to stay on your cool, sweaty toes.
Okay, so they specialize in eating dead human skin, and they love our cool extremities. Following that logic, you would naturally assume that these specific species of fungi that specialize only in humans would cause the absolute worst, most aggressive, most painful diseases.
You would think so.
Right, but I was reading the clinical taxonomy section, and that seems completely backwards.
It is entirely counterintuitive, but ecologically, it's a beautiful demonstration of evolutionary strategy.
So?
To understand this, we have to look at how mycologists sort dermatophytes into 3 distinct ecological buckets based on their preferred host. First, you have anthropophilic species, like Trichophyte and Rubrum.
And those live almost exclusively on humans.
Yes. Second, zoophilic species like Microsporum canis, which normally live on animals like cats, dogs, and cattle. And third, geophilic species like Nannitzia gypsy, which live in the soil feeding on shed animal hair and feathers.
Okay, so we have fungi adapted to humans, animals, and soil. And the paradox is that the infections you get from the animal and soil fungi cause the most dramatic, highly inflamed, blistering skin reactions on humans.
Right.
The human-specific ones cause much milder, annoying, but tolerable reactions. Why does our own specialized parasite go so easy on us?
What's fascinating here is that this is an evolutionary bargain. If you are a microscopic parasite that can only survive on a human host, the worst thing you could possibly do is trigger a massive immune response.
Because then we'd notice it.
Exactly. If you cause a blistering, painful rash, the human is going to aggressively scratch you off, apply harsh chemicals, or seek medical treatment. You will be eradicated.
That makes perfect sense. So the human adapted, the anthropophilic species, they have essentially learned to fly under our immune system's radar.
Exactly. Over thousands of years, these anthropophilic species have evolved chemical signals that actively dampen our local immune response.
Wow.
They can actually mask the components of their cell walls so our white blood cells don't recognize them as a threat. They suppress the inflammatory cytokines that would normally cause redness and swelling.
So a mild chronic infection like a slightly itchy foot that you might just ignore for months or even years,
Yeah.
that's a brilliant stealth survival strategy for a human-only parasite.
It's incredible. But when you accidentally pick up a zoophilic fungus from a stray cat or geophilic fungus from working in the garden,
Those fungi haven't made that evolutionary bargain with humans. We are just an accidental host to them.
right, they don't have the specific chemical camouflage required for the human immune system. So our immune system detects this alien invader, absolutely freaks out, and throws every defensive weapon it has at it.
And that massive inflammatory response is what causes those classic angry, red, weeping ringworm lesions.
Yes. The severe reaction isn't because the fungus is inherently more dangerous, it's just our own immune system overreacting to an uncamouflaged intruder.
That is brilliant, but devious. The ones that are meant for us are using stealth camouflage.
Yep.
And because they use that stealth, they are incredibly good at shifting quietly through our populations, which forces public health officials to constantly update how we track and fight them.
It's a constant battle.
The sources detail a couple of concrete examples of this that I found just fascinating. Let's talk about the wrestling mats.
Ah, yes! Tinea gladiatorum.
Tinea gladiatorum, what a name.
It's a perfect example of a pathogen exploiting specific human behavior. Trichophyton tonsurens is an anthropophilic species, meaning it relies on human-to-human transmission.
And it spreads incredibly well through direct skin-to-skin contact.
Right.
And there is literally no environment with more intense, sustained skin-to-skin contact than a collegiate wrestling match.
Exactly.
This fungus started sweeping through high school and college wrestling programs across the U.S. It got so bad, with over half of some rosters testing positive during a single season, that the CDC had to get involved.
It was an epidemic.
The NCAA actually had to mandate strict pre-match skin checks, disqualifying athletes if they had any suspicious lesions, all because this stealth fungus was hitchhiking across sweaty wrestlers.
It highlights how perfectly adapted these anthropophilic fungi are to our social and physical behaviors.
Hmm.
But there is a second epidemiological shift that is even more concerning, I think, because it shows how these fungi can completely evade our diagnostic
Oh,
tools.
this is the UV light shift, right? Let me
Yeah.
make sure I'm following the timeline here. In the 1950s, the dominant cause of scalp ringworm tinea in American school children was an anthropophilic species called Microsporum aduwini. Now, from a diagnostic perspective, this species was incredibly convenient for doctors.
Very convenient.
Because if you shine a Woods lamp, which is a specific type of ultraviolet light, onto the infected hair, the fungus naturally produces pteridine compounds that glow a bright fluorescent blue-green.
Precisely. It was a rapid, non-invasive diagnostic test. A school nurse could just shine a black light on a kid's head in a darkened room, immediately see the glowing infection, and start treatment.
It's like magic. But starting in the 1960s, there was a massive shift in urban areas. That wrestling fungus we just talked about, Trichophyton tonsurans, began displacing the glowing fungus as the primary cause of scalp ringworm.
And here is the problem.
Yeah, here's the critical realization for anyone listening. Trichophyton tonsurans does not produce those glowing compounds. It is completely invisible under a UV lamp.
Which created a massive diagnostic blind spot. Generations of physicians and nurses had been trained to rely on this quick UV shortcut. So when the dominant pathogen shifted in the population, a medical professional could shine a light on a highly infected scalp, see no glow, and incorrectly tell the patient they had no fungal infection.
Man, if you rely on old tricks for new dominant strains, you will miss the diagnosis completely. It's a constant game of cat and mouse.
It really is.
And it seems like our struggle to physically track them in patients is completely mirrored by our struggle to just name them in the lab. The taxonomic turmoil in the research is intense.
Oh, it's a fascinating conflict between classical biology and modern genetics. For most of the 20th century, we classified these fungi into three main groups based entirely on morphology.
Meaning what their spores look like under a microscope.
Exactly. But in 2017, a large international team led by Dutch mycologist Sybren de Hoog published a complete genome-based revision of dermatophyte taxonomy.
They sequenced the actual DNA and realized that the old visual system didn't reflect their true evolutionary family tree at all.
Not even close in some cases. Organisms that looked identical under a microscope were genetically distinct, and organisms that looked different were closely related.
So they had to reorganize everything.
Everything. Species that used to be called Microsporum were moved because they were genetically closer to Trichophyton. They introduced entirely new genera names like Nenitzia.
And clinicians are furious. I was reading the pushback. And doctors hate changing established names.
They despise it.
I mean, think about it. If you were a dermatologist who has successfully diagnosed and treated a fungus called Trichophyton mentagrophytes for 20 years, you do not want a lab report coming back with a name you don't even recognize.
Especially when the treatment plan, the actual medicine you prescribe, hasn't changed at all.
Right. It causes real practical friction.
You have mycologists who require strict evolutionary biological accuracy, and you have dermatologists who require clinical utility and consistency to treat patients safely.
It's no wonder doctors get frustrated trying to track these fungi, because half the time, the human body itself is throwing up false signals.
Oh, the id reaction.
Here's where it gets really interesting, though. I was reading about the id reaction, or dermatophytid, and I genuinely had to read the paragraph twice.
It's bizarre.
Let's say you have a confirmed fungal infection on your foot. Suddenly, you break out in a horribly itchy, blistering rash on your hands, but when they test your hands, there is no fungus there.
None at all. The id reaction is one of the most bizarre phenomena in dermatology. It's a secondary allergic reaction.
How does that work?
What happens is the fungal infection on your foot breaks down skin tissue, and fragments of the fungal antigens enter your bloodstream.
Okay.
Your immune system detects these antigens circulating in the blood and mounts a massive systemic allergic response.
So the rash on your hands isn't an infection at all?
No, it's a false alarm triggered by the immune system overreacting to the debris from your foot.
So the body is essentially lying to the doctor about where the problem is? And the craziest part is the treatment. If you aggressively treat the actual fungus on the foot, the allergic rash on the hands miraculously clears up on its own, without you ever putting medicine on your hands.
It perfectly illustrates the complex, systemic ways our bodies interact with these specialized surface pathogens. But while the id reaction is just a quirk of our immune system, the sources highlight a much more severe, modern threat that is not a false alarm.
No, this one is very real.
It is a very real crisis that we are actively causing.
You're referring to Trichophyton indotini.
Yes. Officially identified around 2020, this is a highly drug-resistant strain of dermatophyte that originated in India and is now spreading globally at an alarming rate.
And from everything in the research, this global spread is entirely our fault.
Completely. If we connect this to the bigger picture, this is identical to the global bacterial antibiotic resistance crisis, just playing out in the fungal kingdom.
Right?
The root cause of the superfungus is the widespread, unregulated misuse of over-the-counter combination creams.
The ones that mix a potent topical steroid with a standard antifungal drug.
Yes. Cheap, widely available creams.
Which, to a patient, sounds like a miracle cure, right? You put the cream on the itchy red ring, the steroid immediately reduces inflammation, stops the itching, and hides the red rash.
And the patient looks at their skin and thinks, great, the infection is gone.
Right. But what is actually happening on a cellular level?
On a cellular level, it is a disaster. The topical steroid works by shutting down the local immune response. It suppresses the T cells and the macrophages in that specific patch of skin. It basically turns off the body's natural defense mechanism.
Wow.
Meanwhile, the antifungal component in that same cream is often a drug that simply halts the fungus from growing rather than killing it outright.
So you have removed the body's natural army, and you are only hitting the fungus with a glancing blow.
Exactly. Without the immune system's help to finish the job, the antifungal drug isn't strong enough to completely eradicate the infection. The fungus doesn't die.
It survives.
It survives in this chemically altered environment. It learns to tolerate the antifungal drug, and it mutates.
That's terrifying.
By using these combination creams, we are essentially building superfungi in real time. We're giving patients products that completely suppress their immunity while only mildly stressing the pathogen, which is the exact recipe for forcing rapid evolutionary resistance.
It is a textbook case of a convenience product creating a massive downstream public health problem. And now it's spreading. We're seeing strains that are completely resistant to terbinafine.
Which is deeply concerning because terbinafine is our standard frontline oral antifungal drug.
That's our go-to weapon.
Right. It works by interfering with the fungus's ability to build its cell wall. When terbinafine stops working, it forces physicians to use older, sometimes much more toxic oral medications that require blood monitoring.
Just to treat what used to be a simple, easily managed topical fix.
Exactly. And these resistant strains have crossed borders and established firm footholds in Europe and the United States now.
So what does this all mean? If we step back and look at the whole picture, it is clear that dermatophytes are not just a locker room nuisance. They are a live, ongoing case study in evolution, human behavior, and medical history.
Absolutely.
We are watching them actively evolve to evade our immune systems and outsmart our medicines. And the wild part to me is the technological contrast.
No, the agar.
Yeah, we have genome sequencing that is completely rewriting the map of fungi today. We are tracking global mutations of superfungi. But if you go into a modern clinical lab right now to culture and test for one of these infections, they are likely going to grow it on Raymond Sabra's dextrose agar.
Which is a specific nutritional jelly formulated for growing fungi, invented well over a century ago, around 1910.
1910, we are using a 19th century style diagnostic jelly to track a 21st century superfungus. It is such a stark reminder of how some fundamental scientific discoveries stand the test of time, while others completely blindside us.
That historical contrast actually raises a really vital question, and it relates directly to one final story from the research about a drug called grisafulvin.
Okay, lay it on us.
So grisafulvin was discovered in 1939 by researchers at Oxford. They isolated it from a mold called Penicillium grisafulvum.
Wait, let me make sure I'm catching this. Penicillium, as in the exact same family as penicillin.
The exact same genus, discovered right around the exact same time by scientists moving in the same circles.
Wow.
Penicillin, as we all know, obviously went on to change the entire trajectory of human history as an antibacterial drug. But grisafulvin, it was completely ignored as a human medicine.
Really? For how long?
For nearly 20 years, it was studied and utilized exclusively as an agricultural fungicide to protect crop plants from rotting.
So it was sitting right next to the greatest medical breakthrough of the century for 20 years, and we just thought it was for farming.
Pretty much. It wasn't until 1958 that researchers finally tested it properly and realized it was an incredibly effective oral treatment for human dermatophyte infections. The very stubborn, deep-seated scalp and nail infections we've been talking about today.
That's wild.
Once they realized its potential, it rapidly became the gold standard pediatric treatment for decades.
Which leaves us with a thought I hope everyone listening will take with them today. If a fundamental, life-altering medical treatment was sitting right in front of us, completely ignored for 20 years, simply because we had mentally categorized it as agricultural, and if we are still relying on a diagnostic gel from 1910 to track modern pathogens, what other major medical breakthroughs are we currently completely overlooking simply because we think we already know exactly where they belong?
It challenges us to constantly reevaluate our assumptions. Innovation often comes from looking at old things with new eyes.
Makes you wonder what else we're missing while we're staring right at it. Next time you're in the gym shower, give those itchy toes a little respect. They're part of a much bigger evolutionary story.